The next speaker will be Tomoyuki Yamakami, and now we have a right to real quantum computations. So actually he will talk about recursive definition of quantum polynomial-time computability. So Tomo, please.
Okay, well, thank you very much. Oops. Okay, so my talk is all about the quantum computation, and well, the outline of this talk is about quantum computability. Well, particularly this time it's in a polynomial time, the computability. So what I did here is that I just propose a new definition. So that is different from the previous two definitions. Well, I'm going to explain those two definitions. So this is the third possible definition, that actually characterize exactly the same functions computable in so-called polynomial time in the quantum setting. So later, the main topic, main result of my talk is about the characterization. So this definition is exactly characterizing the concept of the BQP. So this is a bounded error quantum polynomial time. Well, this is a language class. And another one is the function version of the BQP, so-called an FBQP. Okay, so just to remind you a few things. So we have functions, standard functions, that is actually defined in the recursive way. So that's those functions are called the recursive functions. Well, some restricted case, primitive recursive functions, right? Those are actually defined in several different models. For example, we have the model called the Turing machine model and lambda calculus model and so on. So those definitions of different models are not characterized exactly the same notion. So we can choose whatever we like whenever you attack the problem associated with the recursive functions, right? So I'm looking at the same kind of flavor in the quantum computation. So every model has an advantage and also the drawbacks, right? The cleanest recursive definition, that is one of the things, and I'm kind of referring to during this talk. So the cleaning actually gave the idea of the defining the function class, giving the initial functions, a small set of the initial functions, and also the way you actually generate the new functions out of the existing functions. So that we can apply this rule, then we actually expand the scope of the size of the functions, and eventually we'll get a whole set of recursive functions, or primitive recursive functions, whichever is the rules you choose, right? So that's the basic motivation. Before going into the details, and I want to give you some flavor of the quantum computation. Some of you may not be familiar with quantum computation, so I just give you the tip of the quantum computation. So I start with the definition of the quantum bit, so-called the qubit. So qubit is the quantum version of the standard classical bits. Well, we just use the classical opposite to the quantum. So instead of having 0, 1, so we have so-called the quantum bit or qubit. We will use the Dirac's a little bit strange notation, 0 kit and 1 kit, or bits 0 and 1, respectively. So physically speaking, so the quantum bit is represented by the kind of tiny particle just spinning around. So then if the spin head goes up, right? So we just simply think this is just a classical 0, and if the spin head goes down, then this is just 1, or the other way around, right? So that's just, the way we think what classical bits are, right? Now, well, this is actually a different model. For example, if you think about the atoms and the electrons, usually it's electrons and orbiting the nucleus, right? Like this picture here. And usually it's electrons stayed in the same orbit. Well, there's several different kinds of orbits. But the very strange thing is that one single electron stayed in that different orbit at the exact same time. Right, so that's the basis of the quantum physics somehow. So there's some strange things going on, kind of thing, right? So basically we have the kind of the mixture of 0 and 1. So we call it the superposition. So in the mathematical term, so that 1 qubit is the linear combination of ket 0 and ket 1. So you think about it, this is actually vector form. Right? 0 vector and 1 vector. So any qubit is the linear combination of those two vectors. And alpha and beta are, well, coefficients, but then we generally call them an amplitude. The amplitude that, well, generate complex numbers. And the size of this the vector has to be exactly 1. So that's a requirement. Okay, so another, the very funny thing about the quantum computation is that basically the quantum information is stored in this, the spinning particle, right? So we have to get the information out of this particle, so we have to look at it, right? But then the problem is an observation or the so-called measurement, right? Just simply looking at this particle, that destroys the quantum state. So what we get is just a classical information with some certain probability. That probability is associated with how close they are. Think about it in the spin head here. The spin head is actually around this area, right? So whenever you look at this one, you only get either 0 or 1. That is, how close they are, right? So that's corresponding to the probability. And another interesting stuff is about it. If you have more than 1 qubit, like 2 qubits or 3 qubits, and you have a very strange correlations called an entanglement. For example, we have 2 particles, they are actually staying in this particular state. So the red color corresponding to the both qubits, and the blue one corresponds to the other qubit, because those are physical objects, so you can actually separate them. You just take one, put it into the safe, and then just bring to the other end of the galaxy, for example. So you can do that because just a simple object, right? But those things are actually correlated in the sense that when Bob look at this, his qubit and then find 0, then the Alice's qubit turn into 0 without even looking at it. So that happens simultaneously, even if the 1 qubit is the other side of the galaxy. So that's the entanglement. Okay, so now we just go back to the business here. So so before that, I just mentioned about the quantum algorithms. Usually the quantum computation is faster than classical computation. There are several evidences, right? Integer factorization, by short, that is faster, the exponentially faster than the existing well-known the algorithm in the deterministic setting, and the database search, right? Even if there is no structure or data structure is assumed, but still the robust algorithm is way faster than the existing standard database search. Okay, so now I just give you 2 definitions. I promised I'll explain the 2 definitions. One of them is the Turing machine model, so-called the quantum Turing machine. So this is proposed by Drake in 1985, And later, Bernstein designed it and expanded it significantly and built a theory based on this quantum Turing machine, right? And what I did, and several other people actually considered the multiple take models in the early days. Oh, by the way, I was staying with Andy Yao. Yao is actually discussing, talking about quantum computation at the time. And he actually introduced, the quantum computation notion into me. So that's the first time when I started, thinking about quantum computation. But that was a way long time ago, anyway. So the quantum Turing machine looks like this. It's more like the standard Turing machine, but the only difference is the way they actually evolve, right? Instead of the standard and classical, the transition function, we actually, modify the qubit system into another qubit system. So this is basically a linear transformation, like the matrix. So you simply apply a matrix. That's it. It's very simple. Okay. So another model is so-called quantum circuits. Well, Deutsch actually proposed this kind of a notion he called it the quantum network. And then later, Yao actually clearly defined the quantum circuit. This is the quantum version of the standard Boolean circuit. And something like this one here. So we have the so-called quantum gates, and then just build up the circuit out of those quantum gates. And so we actually plug in the qubit into this quantum circuit. Then we'll get the different kind of the qubit, and that is the outcome of this circuit. It's very simple. Okay? So now the BQP is the complexity class, the class of languages. That is actually recognized by the polynomial-time bounded data quantum Turing machines in polynomial-time. So that is the important thing. So the BQP is defined by the so-called well-formed QTM. The QTM itself is just a model, but then we have to add an extra condition, so-called well-formedness, because otherwise, the QTM does not define the proper BQP, right? Another model is the quantum circuit, but here is we need the uniformity. Well, even in the classical sense, we have to have some sort of the uniformity, like a P uniform, L uniform, or D time uniform, that kind of things. A similar thing happens here. Right? So we have two different definitions, but then those definitions requires well-formedness or uniformity, that kind of thing. So my motivation is why don't you just to get rid of those definitions, kind of. So now I just go back to the clean is the recursive definitions. So before going into that, I have to give you some notation here. So this is H sub k. This is the Hilbert space of the dimension k, and I'm using the basis state. The S is the strings of length n, the binary string of length n, and H sub k is actually defined by spanned by those the computational basis, right? And I tend to call it the Q string, like a quantum string, right? Q string, like the qubit. And the quantum function is a mapping from those the Q string into Q string. Okay. And but here the terminology, the quantum function is slightly different from what I was considering. It's a long time ago, the paper over there. So I'm just sticking to the function mapping Q string to Q string. Okay. So so more conventional, notational convention here. This strange notation is the corresponding to the measurement. So suppose that we have the tip phi, and then using t as the basis to observe these qubits. Then what we get is some qubits left over this measurement. Because suppose that you have 3 qubits, and you look at the only 2 qubits, right? Then those 2 qubits are will collapse, but the last one still survive, right? So still we have a Q string. Sorry, here, and so here is a new definition. So I start with the initial functions. Those functions are slightly more complex than in the classical case. The identity function, that's very simple, and phase shift. That means we just simply change the amplitude. And rotation, and that means you actually apply the rotational matrix, right? And then negation, that is very simple, flipping the bit, like a 0 goes to 1, 1 goes to 0, right? The standard NOT gate, right? And remove, that means you actually move the front bit into the last bit. And swap is you actually flipping to swapping the 2 strings without affecting anything. And the last one is the measurement, the partial measurement. And as I said, if we have 3 qubits and then look at the 2 qubits, we actually collapsing those 2 qubits. But here is just collapsing just the first qubit. So maybe I'll just looking at the base, the computational basis, right? So for example, then swapping means that all those AIs are actually either 0 or 1. Okay, so we are actually changing the first and the second bit, right? So that's the swap operation. Remove is the first bit goes to the last bit, and so on, right? The measurement is we just look at it in the first element, so it just gone out of the system. So we only have A2 to A sub n. So now the construction rules. We have 3. The first one is the composition. That is very standard. And the branching rule, like we actually can exercise if then else statement, right? If this is true, then we just do nothing. But the otherwise, we just simply apply. Looking at the first element, the first string, Q string is 0 or 1. Then we apply it in the different quantum functions. And quantum recursion. For H2, we simply apply H. Otherwise, we apply G. Here F0 or F1. Depending on the first qubits, right? So first one is 0 here, and the first one is 1 here. Okay, so we have a definition of the initial functions and construction rules. Then we define the class of quantum functions built by those systems, right? So I call it the square QP1, right? And if you just get rid of the partial measurement, because the measurement is the function that actually reduce the size of the vector, right? Like if you have a 3 qubit and then you only have 2 remaining qubits, because then you actually destroy the 1 qubit, right? So the size of the vector in the Hilbert space, or Hilbert space size is getting smaller. So we simply just get rid of this one. So I define the tilde of the square QP1. Well, in the paper, that is actually used hat. Well, just a slight, notational things. Actually, can I draw this, this notation and just paste it, kind of thing. But anyway, so here's an example of the square QP1, the C naught, controlled naught. For example, if you have 0, then do nothing. And then if you have 1, then you just apply negation, for example. So this is the so-called controlled naught. So this is actually simply defined by the branch of I and naught, right? And this is a rotation around zx, right? So this is all simply defined using branch operation. And this is the famous operation called the Marsh and Hadamard operation. So this is actually defined in this way. So this is actually standard definition here, right? It's more like the 45-degree rotation. Okay, so the main, okay, before that, I want to use this strange notation here. Suppose the G is any quantum function defined, the mapping Q string to Q string, and the P is any polynomial. So this notation here is defined in this way. Well, because we have the coding program later on, so I just simply plug in the size of P into before applying G here, right? And also now we use the encoding scheme like this one here. 0 tilde is 0, 0, 1 tilde is 0, 1, then 2 tilde is 1, 1. So the 2 is actually used as the kind of the end marker or separator. Okay. So if you have an S with the binary n strings, then S tilde or x extension of S is the tilde version of all those S of I, and we actually add the end marker at the end. Okay, so here's my main theorem. The main theorem says that the functional version of the BQP is characterized by square QP1, or even tilde square QP1. Well, depending on how to define the target function. So for example, then here is the the function is here. So we just simply take the polynomial that bound in size of f, and we generate this particular quantum state, and this is, so we just simply expand the f so that the size of the two strings are exactly the same, and we simply take the L2 norm, or scale of the L2 norm, and that is corresponding to the probability of observing as an f of x in this quantum state, right? That is bigger than 1 minus epsilon. The epsilon is the constant between 0 and a half. Now, if you are allowed to use the measurement, so you don't need to worry about that kind of thing. So you simply apply here and then take the L2, the size of the oops. Do I make a mistake here? Extension. Well, that's fine. Okay. So then, sorry, I just made a mistake here. Well, here is that we actually taking the size of the vector here, but then here the G actually measure the size of so we just simply to make the size of this guy is exactly the size of an f of x, so that we don't need to worry about the L2 norm. We simply take absolute value here. So that's the only difference between the using the measurement or not using measurement. Okay. So this main theorem is split into the two lemmas. And the first one is the if you have the square QP1 function, then so we can actually build in the standard QTN, well-formed QTN that actually can exactly calculate the outcome of this function, right? So this is just a simulation because then we have initial functions and the construction rules. We start the initial functions are very simple functions, so we can simply calculate them. Right? In the construction rule, like the composition, for example, if you have then one function, another function, then we have two QTMs, we simply combine them, right? So all those simulation results are pretty simple. And the hardest one is, as I said, the key lemmas. The key lemma is, the other way around. So then suppose we have a QTM, right? Using the polynomial-time computable amplitude. Now we have to simulate this QTM using only functions, right? Now, but then the idea is not so hard. Well, but then it's very complex somehow, because if you really write it down, it's all the statements somehow. For example, how to simulate the QTM? So first we have to express the configuration, somehow, the content of the tape and state, the inner state, right? So we have to produce this particular, configuration, initial configuration, using only functions, right? But we can do it. Now we have to simulate the one step of the QTM, so that one configuration is changed to another, right? So now then we have to build a function that take this first, the previous configuration and then generate the next configuration, right? So this is a little bit hard because we have to think about all possibilities kind of thing, but still, we can manage it, right? Theoretically. So after this, we proving the main theorem, then we can actually prove the normal form theorem as a sort of corollary, right? So this says the we have a particular function that simulates all functions in certain way, like the universal Turing machine sort of thing, right? Okay. So to conclude my talk, I just present two possible applications of this recursive definitions, right? The first one is the descriptional complexity, because we have initial functions and the construction rules, and we can think about this is the the count and the number of the steps to produce particular function, right? For example, the initial functions. Right? So we only need one step, right? But then if you use composition to produce a function, that takes two, right? So on. So we can actually define the complexity of the function in terms of how many times we actually use those gadgets, the initial functions and the rules, right? So that's the one thing to think about. I haven't really explored this particular notion yet, but this might be a possible application. The second application might be we just simply go higher up, in the sense that the higher types, right? In the recursion theory, we have the notion of the types, like standard functions are called type 1, but then if you use the type 1 function as a sort of an oracle or an external device, and you can access it to enhance the computation, so you have a type 2 computation, or type 2 functions. So we can do the same thing, and then we can possibly develop higher type, or second type, or third type, higher type functions, quantum functions. So that might be the possibility. Okay, well, thank you for listening, and I'm happy to take your questions.
Thank you. Questions, remarks? So let me start first.
Okay.
You have shown like 3 alternative type of descriptions.
Mm-hmm.
The first was like quantum Turing machine, and then quantum gates, and then the third one that you introduced this like
yes,
expression
mm-hmm.
type.
Mm-hmm.
Which is closer to the practice of quantum computing?
Well, probably none of them, I guess. Well, because the physicists and engineers, they actually try to come up with new ideas on how to build quantum computers. Like now, the Googles and other companies in Canada, they try to build the quantum computers, actual quantum computers, and spends a lot of money hiring researchers. But they're actually looking into something different. Well, think about it in the classical case. We have a Turing machine model, but how cool that model is, the real computation, like computer here, right?
Yeah, that's a good idea. Okay. Other questions, remarks? Thanks again.
Okay, well, thank you very much.